Okay, good evening, guys. Sound check, screen check. 如果听到全部 OK 的话，给我一个 thumbs up, and then we'll start. Okay. Okay, now 你们的 test cancel 了哦，是换去什么？换去 homework. OK，因为上次我教到那个 gravitation 是不是 gravitation？But 上次我没有讲到那个 Kepler's Law，所以今天我要讲完它啦，讲完那个 gravitation 了，也不要好像半天掉这样子，所以我会讲到 Kepler's Law。OK，after we finish the chapter for gravitation，and then I'll give you some revision exercises for the previous chapters。OK，其实我们现在已经是在forces and pressure。OK，上几个星期我教的那些是the Pascal Archimedes principle. Okay, so you have all the videos recorded. You can just watch it anytime if you forget or something like that. OK，可是有一个那个 Archimedes principle 的，好像是有一 part 是我忘记press record 的，所以它有一点点 missing 那一 part 啦。OK，可能我再看回去，我再做的一个 extra video 放上去 ，just in case 啦。OK， for revision purpose or something like that. OK，now 还有的就是什么我们已经在 forces and pressure，so we'll come back a little bit. OK，so that we don't move too fast. We try to follow the pace of your school progress. OK，but actually your school progress is a little bit slow. Alright, because now is in July, right? In July, you should be at forces and pressure at least. OK，因为我也是问了Mr. Lim，Mr. Lim 他也是跟我们讲progress 有点 slow， 可能是因为 MCO 那种 online stuff 啦。Alright, so never mind. We'll come back and do a little bit of exercises. After I teach the Kepler's law, I will give you a little bit of exercises to practice. Okay? Now, now let's start this one. OK， 如果有什么断线还是不清楚，听到不清楚，记得跟我讲。OK， feel free to stop me. All right. Okay, now Kepler's law still about the planetary motion. Okay, the celestial object in the universe. Now Kepler's law actually came from a person's name. His name is Kepler lah. All right, so the scientists they always use his name lah. They always use their own name for the what they discovered. So Kepler's law, his name is Kepler. Okay, now he has actually 它有3个 law that governs the universe. Actually, it means that how does the universe, the motion of the planet moves. All right. Now, just to tell you a little bit about how this Kepler's law came about. All right. Now, very long time ago, a century ago, right? They actually believe all the people they actually believe the objects in the universe, right? The Earth is at the center of the whole universe. Okay, Earth is at the center, and then everything else revolve around the Earth. All right, in perfect circle. Okay, so if I draw this out, it looks like this one. So this is the planet Earth, and then they actually believe that all these objects, right, revolve around the Earth. Even the sun also revolve around the Earth. Okay, and not only they revolve around the Earth, they actually move in perfect circle. Okay, now after that, a few years after, over the years, then they come up with a lot of these theories, right? And you have heard about some of the theories. Even now, also you have heard about some of the theories. For example, like the flat Earth theory, right? Some people they actually believe. I don't know is really they believe or they just want to make fun. All right, is that they say that the Earth is flat, right? So which is quite ridiculous, right? With the evidence that we have nowadays, okay, it already proved that Earth is not flat, of course, right? So a lot of theories, right, has been coming up in the past years. Okay, so they actually like after a few years, after these ideas prolonged for a few years. So one scientist, he came up and he says that, okay, now the actual case is not like this. Okay, so the actual, the true correct positions of the universe is that the sun is at the center. Okay, and they call this idea the heliocentric, right? So before this idea came up, the earth is at the center, they call it geocentric. Okay, geocentric universe means that the earth is at the center, right? Now heliocentric means that the sun is at the center and every other objects, including the earth, revolve around the sun. Okay, but many people, turn out that many people, they didn't believe this idea. Okay, they still stick to geocentric. Okay, now what happened is in the 15th century, it's like 15多年啦，1500年 okay, there's one scientist, right? His name is, I think is Taco. His name is Taco, Tacho. Okay, now this guy, he's actually a very good in measurement. Okay, this Taco is very good in measurement, and he's a scientist, he's a mathematician. Now he came up with a lot of calculations, okay, to show that the real positions of the planet in the universe. All right, of course he has a lot of these devices, okay, and at that time telescope was already invented, right? The telescope already invented, and they can somehow get a clear idea, a clear image of where are the planet located, okay, where the sun located, where the earth located. So this guy, this Taco, right, he managed to come up with a very quite accurate model of the universe. Okay, he knows exactly what is the position of the earth, what is the position of the sun. Okay, and over time, okay, over time, what happened is that he gradually improved his instrument, okay, just to get more precise reading of the positions of the universe, the planet in the universe, right? But still, at that time, many people still didn't believe that. All right, many people still believe that. Now, what happened is in the, I think 16th or 17th century, I forgot lah. All right, this guy, the Taco, like before he died, okay, before he died, he passed on his work, all his calculation, all his project to his co-worker, okay, which is also a scientist. And this scientist, his name is Kepler. All right, 就是这个人啦，Kepler. Now Kepler is his co-worker. Okay, now Kepler got all of his reading, okay, got all of his research, and then somehow Kepler he saw there's a pattern in his research. Okay, there's a pattern, and this Kepler is also a very good mathematician. Okay, and he was able to put up all the pieces together. Okay, so he looked at the measurement Taco made, and then he put all the pieces together, and he formed these 3 laws of the universe. Okay, which is we call the Kepler's first law, Kepler's second law, and Kepler's third law. 就是很像 Newton 这样啊，Newton 也是有 first law, second law, and third law, right? Okay, now we are going to look at what are the laws. What is the first law means? What is the second law means? And what is the third law means? So until now, the Kepler's law still applies, and like thousands of experiments has been carried out to prove that it really exists and it is taking place right now. Okay, now, okay, back to this one. Okay, just a little bit of history lah. Just now that one lah. Okay, not important lah that one. Okay, now Kepler's first law. Let's look at Kepler's first law. Kepler's first law of planetary motion. Okay, now Kepler's first law, he says that, let me write this down. Okay, it says that orbit of a planet is an ellipse with the sun at one of, I think it's at one of 2 foci. Okay, now this is Kepler's first law. It says that Okay, the orbit of a planet that revolves around the sun is actually an ellipse. Okay, if you remember just now I said over the years people have been believing the orbit is actually perfect circle. Okay, so Kepler found out that from Tycho's measurement, he found out that the orbit of the planet is actually not a perfect circle. Okay, it is an ellipse. All right, and with the sun at one of the two foci, what does that mean? So if you look at a circle, right? Let me draw a circle here. If you look at a circle, so circle, we have a central or focus, which is the center of the circle, right? Now, for an ellipse, ellipse simply looks like a squashed down circle. Okay. Now, this one like oval shape. So for ellipse, it has two foci. Okay. Now I'm going to bring a new term here, which we call the eccentricity. I think maybe you have heard about this one. Okay, eccentricity is simply a measurement of how close is the foci. Okay, just imagine this one. If you look at the ellipse, these two foci and the equilibrium position, the center position is this one, the dotted line. Okay, the closer the two foci are, okay, the more circle it is. Right? Just imagine if these two foci is bring close together, then it forms a perfect circle. Okay, so if the foci is being stretched out, then slowly it becomes squashed down, it becomes oval shape, ellipse shape. Okay, so that is eccentricity. Eccentricity simply is a measure of like how circle 有几圆啦，有几圆一个东西有几圆，那个就是 eccentricity。OK， so eccentricity 如果它靠近零的话哦，它是零的话，它就是圆形。OK， 如果它靠近一，它就越来越像 ellipse 这样子。OK，now so this one it says that orbit of any planet revolving around the sun is actually an ellipse. That's all. That's the first law. OK， now 如果你看我们的Mercury Venus Earth and Mars, right, orbiting around the sun, right, the eccentricity of the orbit, right, is close to circle actually, but it's not really, it's not in actual case lah. Okay, let me write this down. This shows all the planet, right? Our Mercury is almost, eccentricity is almost 0.206. It's quite close to zero, so we can say that the orbit is almost circle, but not completely. Okay, in the actual case, it is not circle, but some people just assume that it is circle. Okay, if you look at compare with Venus, we have like 0.007. It's a lot closer, right? Closer to zero. And then we have Earth. This is our orbit. Our orbit is about 0.017, and also Mars. I think it's around 0.093. Okay, so if you look at the orbit of our planet, of the solar system, it is quite low, the eccentricity, and it is quite in circular shape. All right. Now, second law, Kepler's second law. So after he formed his first law, what is his second law? Second law, he says that okay, 我写下来的那个 a line segment joining a planet and the sun okay, so this is the okay, let's look at this one. Okay, second law, it says that a line segment joining a planet and the sun sweeps out equal areas during equal intervals of time. 什么意思? Okay, now let us draw the orbit of this is the sun. Okay, and then this is our This is our, okay, this is the, okay, this is our Earth, and this is our orbit. Now, when the Earth revolves one circulation around the sun, right, is like 365 days 一年, all right? Now, second law 啊，它就是在讲着 our Earth, right, any planet that is revolving around the sun, right, it does not always move in the same speed. Okay, 意思说这个 Earth 啊 when it is further from the sun, 就是这里 from point, let's take 2 points. This is point A and point B. When it is further away from the sun, okay, is moving with slower velocity. It's moving with slower speed, and it actually catches up speed when it is closer to the sun. Here, closer to point A. Right? So at this point, it's closer to the sun, so the Earth will actually speed up. All right, so this is what second law says. Now, to be exact, it means that 如果我 treat the sun as the center, okay, 如果我画一个 sector 在这边 like this is a sector, okay, and then I draw another sector connecting all the way to here. Okay, let's use a different color, black. Another sector connecting here to here, okay, and then the area of the sector is the same. Let's say this is A1 and this is A2. Okay, now A1 equals to A2. Okay, so if it sweeps up equal areas, these two equal areas, then from 2 points, let's say this is from A to B, point A to point B, and then the other point is point C over here to point D. Okay, the time taken for the Earth to move from point A to point B is the same as the time taken from for Earth to move from point C to point D. This is what the second law means. Okay, now I repeat. Okay, for equal area of sector, okay, and then we plot a point A, B, C, D here. The time taken for the Earth to move from point A to point B is the same as the time taken for Earth to move from point C and point D. Okay, now so A 跟 B 哦，它的距离是比较远。Here, the arc is further, is bigger. Okay, C and D, the distance is shorter. Okay, so in order, if the Earth, if the time taken move from A to B must be same with the time taken from C to D, meaning that the Earth must move faster from A to B, right? Simply because A to B is longer, the distance is longer, so that the Earth has to move faster so that it reach point B at the same time at the other side. Okay, at the same time as from point C to point D. Okay, so this is basically what the second law means. Now, 如果你讲 apply the second law for Earth, right? Because the eccentricity of the Earth, just now we talked about the eccentricity, right? So how circle is the orbit? Look at Earth. How much is Earth? 0.017 is like close to 0. It's like almost circle. Okay, so the second law does not really mean much for the Earth or for any planet like Venus, Mars, because the eccentricity is very small. It almost look like a circle, right? But it is going to be useful for what else? Comet. Okay, comet. Okay, like I forgot in what year, there's one comet, they call it the Halley comet. Okay, so this comet revolves around the sun. Okay, Halley comet. Actually, this comet, the eccentricity of its orbit, it's about like 0.96 something. Okay, 96, I think 967, 96 something. So it's very close to 1, right? So it is like ellipse shape. like a perfect elliptical shape. Okay, so it's going to be useful for this one. So the scientists, they actually found out that this Halley's comet, okay, when it is closer to the sun, it really moves faster. Okay, they did all the calculation and stuff like that. Proven is proven. All right. So this is Kepler's second law. Okay. Now, third one is Kepler's third law. Okay, 我擦掉这个线. So if you want to take a screenshot, you can just take a screenshot. I still got record down this one. Okay, now let me just erase this one. Okay, now Kepler's third law, what does the third law say? Okay, the square of the orbital period of a planet is proportional to the cube of the semi-major axis of its orbit. Now, orbital period, 这个是什么 orbital period 我讲过就是 the time taken for one orbit, right? So it's like for Earth, it's like 365 days. Okay, so the symbol is T, right? And then this T is proportional to the cube of the semi-major axis. So if you look at a ellipse, this is the semi-major axis, and the horizontal one is the major axis. Okay, actually it is referring to the radius lah. Okay, to make actually is referring to the distance of the planet that is revolving around the sun. Okay, the radius. Now this third law, it means that, let me draw this out. Okay, let's say this is the sun. 1, 2, and 3. Okay, first one, and this is our Earth here. Okay, now basically the third law says that if I have two planets revolving around one object, the sun, the radius of the first planet, this one, okay, I use a red color, the radius of this one over here, let's label it as R1, and its period is the first planet, the time taken for the first planet to orbit around the sun, right? So I label it as T1. Okay, and then we have another one, the planet Earth. So another radius over here, R2, and then also T2, the period of the Earth. Okay, now what you have learned in the previous class is that for any orbit in the universe, in the space lah, okay, for any type of orbit, the gravitational force equals to what? The gravitational force equals to the centripetal force, right? You have learned about this, right? So it's like it works for the satellites, for the moon, anything that is orbiting around another object. The gravitational force equals to the centripetal force. Now let's break it down. This one, gravitational force, you already know that it is Gm, G big M and small m, Gmm over R square, right? Centripetal force is like mv square over R. Okay, so let's cancel out the m, cancel out the m. Now, V we can express into circular motion. Velocity, the general formula is distance divided by time. Okay, so since in orbit it is moving in circle, so the distance of circle is the circumference of the circle. So it's 2 pi r. Okay, 2 pi r. And then the time for one circle, we just put the capital T, stands for the period. Okay, so if you put this in this formula, you slowly derive and then you will get what? You will get this one. Okay, you derive and then you will get 4 pi square r cube over gt square equals to m. Okay, this one actually I show you in the previous lesson. Okay, if you've got write down the notes, then you can derive this one. Okay, so you just substitute inside the value, and then this m is the mass of the sun in this case. Okay, now look at this formula here. You see there is r cubed and then there's t squared, right? So if I bring all of this to the other side, so that I get like gm divided by 4 pi square, that will be equals to r cubed over t squared. Okay, r cubed over t squared. Now, what is this value here? You'll notice that this g is a constant value, right? And this mass, if the planet is revolving around the same object, then this mass is the constant, is the mass of the sun. Okay, it's the mass of the sun. And then at the bottom, the denominator, this one is also a constant, pi is a constant. So overall, this thing is equals to constant. Okay, so from here, we can say that the r of the first planet, cube root, divided by the period of the first planet, square root, is the same as the r of the second planet, cube root, divided by the period of the second planet, square root. This is Kepler's third law. Okay, so what is Kepler's third law? This one. You just write down this formula. Okay, so this is what, basically this is what the sentence means. The square of the orbital period of a planet is proportional to the cube of the radius of its orbit. Okay, now, so if you look at this one, right? Okay, let me show you one thing here. So this one, the ratio of r cubed divided by t squared is actually the same as the r cubed of another planet divided by t squared of that planet. So let's prove this one. You see, this one, actually we got, I write down, wait. Let me bring this up. Now this one over here. Okay, so what is the formula again? R1 cube T1 square, right? Equals to R2 cube and T2 square. This is the formula. Okay, now on the left side, you see a table, right? This table shows the actual value of the period and then the distance of each planet in the solar system from the sun. Okay, so if you look at Earth in the third row here, so we have like 365.2 period, and then the distance of the Earth from the sun is 149.6. Okay, now if you calculate this one, r cubed divided by T1 squared, let's calculate for the Mercury. For the Mercury, so you have r cubed is 57.9 cube. Okay, we don't have to put the, okay, let's just put the what times 10 to the power 6 cube divided by the period is 88 power of 2, right? So what do you get this one? This one you will get, let me just calculate for a while. And then power of cube divided by 88 square. So you will get like 2.51 times 10 to the power of 19. Okay, 2.51 times 10 to the power of 19. So if you calculate, repeat the same process for all the other planets, for Venus, Mars, Jupiter, you will still get all the same value, 2.51 times 10 to the power of 19 kilometer. So all this will equals to the same value. Maybe there's only slight difference. Okay, so this Kepler's law, third law, it proves that R1 cube divided by T1 square will be equals to R2 cube and divided by T2 square. Okay, so what is the usage of this formula? Like, so what? Right, so what is the usage of this formula? Now, let's look at a few examples of calculation. Okay. Okay, let's look at one example here. Okay, just give me 1 minute to type it out. Okay. Now the mean distance between the Earth and the Sun is 1.5. This one. Okay, so let's draw it out. The Sun is the center. Okay, I just write S, and then the orbit. Okay, so the distance is, okay, I forgot one more. Let's draw the Mars. Two orbit, right? Two orbit. Okay, two orbit. And okay, so the first one, Mars. Earth and Mars. Okay. The mean distance between the Earth and the Sun is 1.5. So the radius labeled here, the radius over here is 1.5 times 10 to the power of 11. And the mean distance between the Sun and the Mars is 2.27 times 10 to the power of 11. What is the period of Mars around the Sun in Earth days? Then you use the formula to calculate. Okay, so this is, we calculate using the Kepler's third law. So this is 1.5 times 10 to the power of 11 meter. And the distance from this one, 2.287 times 10 to the power of 11 meter. So the period, what is the period of Mars? So you want to find T2 squared. So R1 cube T1 square equals to R2 cube T2 square. Okay, so 1.5 is radius of the Earth divided by, so period is not given, but period, you know that Earth is 365 days, right? 365 days. Now, we don't have to worry much about the unit. Why? Because we are calculating the relationship between these two. So we don't have to like really convert to the SI unit, okay? So we don't have to convert the 365 days to second, because we are only interested in the relationship, okay? Because the unit will cancel out each other, all right? So this one, R2 is 2.287 times 10 to the power of 11 divided by T2 squared, right? So this is to calculate, used to calculate the period and also the distance given any two planet, right? So you can just find T2 from here, okay? Same thing. So the same formula also can be used to calculate the mass of the Sun. For example, number 2, calculate, some questions they might ask you, calculate the mass of the Sun using the Earth-Sun. The Earth-Sun mean distance of 1.5 times 10 to the power of 11 meter. Okay, so the formula here is just now that one, m Sun, what is the formula? Equals to what? 4 pi 2 r cubed divided by gt square, right? Okay, so this one, r is the distance of Earth from the Sun, and this is the period of Earth. Use this formula over here. Okay, so this one is linked to this one, almost the same. It's just derivation.